Hi everyone, and welcome to our 16th Inspiration Exchange session. Today's topic is Discovery Using Machine Learning. My name is Nick Maxfield. I'll be moderating today's session, and I handle the Schaar Lab's communications. I'm also joined by Mihaela Schaar, who will be leading today's session, and by two of our Ph.D. students, Zhaozhi Qian and Krzysztof Kacprzyk. So just to give you an idea of what to expect from today's session, as always, our ongoing aim with Inspiration Exchange is to share and explore the breadth of topics in machine learning for healthcare and to generate new ideas for future research avenues. In our previous session, our focus was on interpretability, specifically new frontiers in interpretability. This was a very successful, interactive, free-thinking session in which we challenged some of the existing ideas about interpretable machine learning and introduced some new research avenues. If you haven't already had a look at this, do check it out on our YouTube channel or on our website. Today's focus, however, is on a brand new topic, which is discovery using machine learning. This is a new and very important research area for our lab. So to break this session down for you time-wise, after my short introduction, I'll be handing over to Mihaela, who will give a very quick overview of this new research area, explaining its importance. And then I'll hand over to our PhD students, Zhaozhi and Krzysztof, who will give live presentations on specific approaches to discovery using machine learning. We'll then have our usual Q&A and open discussion. And as I mentioned, this is a brand new research area, so it's really something we want to get your questions and opinions on. So please do post your questions into the Inspiration Exchange Slack channel. The earlier, the better. And if you haven't joined that Slack channel yet, please do so. You can find the URL in any of my previous emails about Inspiration Exchange. So just follow the Slack link to join our Slack channel and ask your questions in the Inspiration Exchange channel. Then at about 5, we'll wrap up with some closing words. But without further ado, please let me hand over to Mihaela for her quick kind of presentation and overview where she'll be introducing this new research area. And if you do have any questions for Mihaela, please put them into the Slack chat. Thanks very much.
Thank you very much, Nick. Welcome, everyone. I'm really delighted that we are going to discuss in this session what I believe to be at the cutting edge of machine learning in healthcare. When I give talks about our lab's research, I often say that I believe that machine learning can transform medicine and more generally healthcare in 6 different ways: delivering precision medicine, understanding the basis and trajectories of health and disease, empowering healthcare professionals and patients, informing and improving clinical pathways, better utilization of resources and reductions of costs, forming public health policies, and enabling new discoveries. But until today, I had very little to show to back up my claim that machine learning can indeed transform medicine and healthcare by enabling new discoveries. Most of the work that our lab has done, but I would generally say the machine learning community has done, has focused on the first 5 advances. However, we really are excited today to tell you how we believe that machine learning can indeed enable new discoveries, and why I really believe that this is really a new frontier for this area. So I want to thank very much to Krzysztof and to Zhaozhi for leading the way in this area and telling you our thinking. And I hope that you all can interact with us and engage with us in these 2 topics. Thank you.
So our first of our 2 presentations is by PhD student Zhaozhi Qian. This will be given live. It'll be roughly 20 minutes. And again, if you do have any questions for Zhaozhi, please post them into the Slack chat. You don't have to wait until the Q&A session to do so. The earlier you post them, the better. So Zhaozhi, if you're ready, please go ahead and share your screen.
Thanks again, everyone, for participating, and thanks, Mihaela, for the great introduction. I'm Zhaozhi, and in this part of the presentation, I'm going to show the recent advances in discovery of governing equations using machine learning. And in the presentation, I will show the importance and the challenge of discovering governing equations, especially through the in the application of healthcare. I will also discuss the limitation of the traditional approaches for discovery, including the expert-driven approach and the restricted function class approach. Then I'll proceed to show why the current currently widely used machine learning methods are not well suited to address the challenges we encounter in discovery, and where is the gap. Finally, I will show our perspective on the discovery agenda and show some recent progress in the machine learning literature to address these issues. So for centuries, scientists have been discovering different sorts of governing equations to describe the natural phenomena we observe in the world. And this phenomenon ranges from the microscopic quantum interactions to cosmological scale formation of galaxies. And indeed, much of the scientific research is conducted with the goal of finding compact and closed form equations to describe the world. And these equations come up with all sorts of different forms. For example, the explicit function y equal to fx can help someone to make prediction directly. The implicit function, on the other hand, encapsulates conservation laws and symmetries. There are also classes of differential equations that help us model the temporal and spatial aspects of the phenomenon. And all of these falls into the category of different governing equations, and we're going to discuss today. And just a brief side note that we're not going to discuss the discovery of drugs or molecules, which is also an important subject. So for those of you who are familiar with discovery, it is helpful at this stage to clarify what is the difference between causal discovery. So in causal discovery, the key goal is to identify the causal graph, which encapsulates the causal interactions between the variables. And of great importance is the direction of this causal graph, whether variable A has a causal effect on B or vice versa. It can get quite complex as there are as more variables are included, as suggested in this illustration. However, in causal discovery, the discovery usually stops after the skeleton of the causal graph is fixed, rather than coming up more quantitative relationships. On the other hand, in the discovery of governing equations, we not only care about the relationship, the qualitative relationships, but also care about the exact equation. And this has some connection with the so-called structural equation model in causality. And indeed, if we have the governing equation, one can read the causal interaction graphs from the equations directly. And so far, I've been presenting several examples in physics, but governing equations are also very important in healthcare. And here I just give several additional examples to contextualize its importance. And the first example is in pharmacology and physiology. Some governing equations have been proposed to model and predict dosage response and absorptions of drugs. And for example, the Hill equation in pharmacology. And these equations can help design optimal dose for a certain drug. And in the literature of disease progression modeling, governing equations have also been used to model tumor growth under different treatment effects. An example is shown here in a recent paper. The governing equations also have been used to model in risk prediction applications for modeling disease-specific mortality. And finally, these type of governing equations have also been used in epidemiology to model the spread of epidemic. And there are, of course, many more applications of governing equations in healthcare. And now I'm going to talk about the traditional approaches that have been used for quite some time to discover the governing equations. And of course, as we all know, the most common way of discovering this equation is through the human expert. And I will refer to this approach as the expert-driven discovery. So in this paradigm, the human experts or scientists discover the governing equations based on their domain knowledge scientific intuition, and personal experience. And here, the expert plays the key role. And it is no wonder that many natural laws and physical laws are named after the scientists who discovered them as a recognition of their contribution. In comparison, the data only takes supportive or marginal role in providing inspiration for the experts, providing tools for validation and calibration for the numerical constants. And these characteristics of expert-driven discovery actually brings immediate limitations. To start with, this way of discovery is very intensive on human resource. We need to recruit scientific experts to perform the discovery, and it usually have a very long development cycle, and it's very time-consuming due to the manual works involved. On the orthogonal side, it is also quite difficult to deal for this approach to scale with many variables because it is challenging for humans to disentangle the effect of interacting variables, let alone to find the exact functional form to capture these interactions. Here I will show an example of these limitations in the modeling of spread of COVID-19 with early data. So at the beginning of the pandemic, the policymakers needs an actionable model to inform policy decisions about intervention policies. And this application has a very high emergency and requires very fast response from the modeling community, which is in conflict with the long development cycle typically implied by the expert-driven approach of discovery. At the same time, this application also involves many variables. For instance, there are many possible intervention policies ranging from national lockdown to universal masking that is available for the policymakers. There are also data sources that have not been traditionally included in the epidemiology models. For example, the data from mobile tracking, which can be used as a strong surrogate for contact rate. And our lab has a prior work to address this application. But I will not give too much detail here. In addition to the expert-driven approach, there is another traditional approach to discover governing equation. And this is what I call the restricted function class approach. So in this approach, the model heavily restricts the model class to be, for example, a linear model or a point-based scoring system. And examples include, for instance, the Cox model for survival analysis, the Charleston's comorbidity index, SOFA score, Glasgow coma score, and so on. So the advantage of this approach is that the resulting model is very highly transparent. It is very easy to fit on new data sets, and it's quite easy to use by the frontline clinicians. However, the drawback is that these restricted models are often only a crude approximation to the underlying governing equation. And it usually ignores interactions between the variables and nonlinear effects. So let's turn to the machine learning literature. So after examining the currently most widely used learning models, we found that they are actually adequate to address the challenges in discovery. And the most widely used machine learning model has 4 key properties that makes such endeavor difficult. And I will discuss them one by one. So first of all, the current machine learning models are usually heavily data-driven, and it requires high-quality training data. And by high quality, I specifically mean that the training data needs to have large volume, very low sampling bias. It should have clean label and measured with relatively low noise. And however, this is often unrealistic to achieve such high quality data in many healthcare applications and beyond. And this puts kind of a limitation on the machine learning fields. And this is actually an active research area in machine learning to figure out ways to effectively learn in low sample and high noise regime. The second property is that probably as we know for now that many machine learning models lack transparency, and they typically uses the so-called function approximator, for instance, trees or neural networks. And these function approximators are aimed to approximate the governing equation rather than discovering the symbolic form of the governing equation. This means that the resulting machine learning model are often uninterpretable. One plausible approach is to perform post hoc explainability to extract more interpretable information from the trained model. But this is still a research frontier. And our group has also some prior work on extracting, making uninterpretable machine learning models interpretable, shown here. The third property of these machine learning models is that they often operate in a fully automated way and keeps the human completely out of loop. Now, this is good in terms of reducing human cost. It also makes it difficult to incorporate domain experts' knowledge. And in many healthcare applications, such prior knowledge are often exists, and we do want to warm start learning with our existing knowledge. And I want to highlight that incorporating the existing human knowledge actually is beyond simply designing a new neural architecture or adding Bayesian prior for certain model parameters. And because here we also care about the functional form that we knew about. And our labs has some prior work on to address this issue specifically. And finally, most of the existing machine learning algorithms are completely agnostic about the data collection. So they are totally unaware about how and where the data is collected from. So the algorithms trained on biased data will likely to inherit such bias. And the algorithms trained on noise corrupted or data with error will be less accurate because it also inherits the error. Moreover, most common machine learning methods assumes that the data set is fixed and is given, and they do not attack the problem of actively collecting more data, except for several specialized methods in the literature of active learning and reinforcement learning. So before going further, I wish to recap the significant challenges for discovery. So especially in healthcare applications, I think the key challenge is that there are many interacting variables and possibly with unidentified mechanisms. The training data that we draw inference from are often scarce and have noise in the measurements. We usually have some imperfect prior knowledge, but this knowledge can often be inaccurate, or it might omit certain important variables. The data set are potentially biased, and sometimes it may be difficult to collect experimental data. And given these challenges, one may ask if this problem is even tractable. And here I analyze two situations. So the first situation is an application with many variables. And as a reminder that this situation is even difficult for human experts to construct governing equations when there are many variables. And one plausible approach is to combine the discovery with some pre-processing steps, such as variable selection. Or we can take an incremental step to incrementally update an already existing imperfect equation by trying to incorporate additional variables. And finally, another promising approach is to use symmetry or other properties of the data set to decompose the problem into smaller pieces and solve the problem in a divide and conquer way. And I'll talk about one example later. Another challenging scenario is for applications with unobserved or latent variables. And this is, again, very common in healthcare. And first of all, wish to highlight that sometimes what we can do is to find the best equation with available variables. And in some applications, this is will already turn out to be actionable. Another direction is to have an adaptive algorithm that adaptively acquire new variables. And this is especially helpful if we have capability to perform experiments or collect additional variables. Finally, there are also like works that uses latent variable models, and is actually a research frontier in machine learning to construct more structured latent variable models in order to inform these unobserved quantities. So now I'm going to present our conceptual workflow of recursive machine learning and discovery. So in the first step of this whole loop, we need to encode, using some algorithm to encode the existing equations and laws or expert beliefs in a machine operable representation. And then with the help of automated algorithms, the experimenter can acquire new data points or variables to challenge and augment the existing knowledge. After the data set is acquired, the automated algorithm may help the expert to refine and update the equations based on new data. And then these refined equations can be subsequently updated again, for instance, addressing the certain illy modeled subpopulation and regimes with high uncertainty. And I want to highlight that this approach is a multifaceted problem, and it will require multiple components. And we do not expect to have a monolithic algorithm to solve all the aspects. However, a helpful way to think about this whole problem is through the lens of optimization. So conceptually, we will treat it as a optimization problem, and the quantity being optimized is either the experimental design, which says which variables to collect and from whom to collect these variables, and also the symbolic form of the governing equation. However, either both the experiment design and the symbolic form of the governing equation lives in a large and discrete search space, and is a very challenging optimization problem. And the optimization problem also involves the objective function. And for discovery, we want to optimize the goodness of fit to the training data, and also while controlling the complexity of the equations so that we obtain a compact and understandable equations at the end of the day. When experiments are possible, we also need to factor in the cost of the experiments. And when there's domain knowledge, such knowledge is often reflected as constraints or priors. And this makes the whole optimization multi-objective. So we are simultaneously want to optimize multiple criteria in order to find the correct governing equation. And multi-objective optimization is also a challenging problem. So here I will review some recent progress in machine learning that is relevant to that furthers the discovery agenda. So most of the recent works focus on developing better optimization algorithms for discrete search. A promising proposal is to leverage reinforcement learning, and especially policy gradient methods to deal with discrete structure. Researchers have also proposed to use encoder networks and recognition networks to infer the unobserved equation from the observations. And these approaches are often combined with pre-training. A separate line of research is to develop better heuristics, search heuristics, to make the search more effective. A prime example is the work of AI Feynman, which proposes to use composition rules and of the equations to divide the main problem into sub-problems and solve the and find the equation in a divide and conquer manner. Finally, there are also proposals to use generative models that generates plausible candidates for multimodal optimization. And however, these aspects are of the recent works in machine learning literature kind of only focus on the discovering explicit function as a prediction tool. But they don't actually talk about discovering differential equations, either ODE or PDE. And these methods are also usually validated on settings with low noise and abundant data, whereas we care more about the high noise and scarce data setting. And this is what motivates us to perform research, motivates our recent research in the decode, which is a novel method to discover ordinary differential equations from irregular time series data. And with that, I can hand it over to Krzysztof, who will discuss the decode work in more detail. Thank you.
Thank you very much, Zhaozhi. So as Zhaozhi mentioned, the next presentation is from Krzysztof Kacprzyk, one of our PhD students who joined the lab last year. This is going to be about 15 minutes. And again, if you do have any questions for Mihaela, for Zhaozhi, or for Krzysztof, please post them into the Slack chat. Thanks very much. And Krzysztof, whenever you're ready, please go ahead and share your screen.
Okay, so hi everyone. So today I would like to present one of recent papers from our group titled Decode, Discovering Closed Form ODEs from Observed Trajectories. And this paper was authored by Zhaozhi, me, and Mihaela, and has been recently accepted for ICLR 2022 as a spotlight. So, as Zhaozhi has already mentioned, we believe that discovery is an important and slightly overlooked area of machine learning. We wanted to explore one possible approach to it, which is discovering closed form governing equations. So equations that are expressed as a finite sequence of some allowed operations, input variables, and numeric constants. They have many benefits over the standard machine learning models like neural networks because they are concise, transparent, interpretable, and what's very important, can be further analyzed by human experts. Also, as physics has showed us multiple times, this kind of equations have usually very strong ability to generalize outside their initial domain. In our research, we wanted to focus on one specific kind of equations called ordinary differential equations, abbreviated to ODEs. An ODE links the function and its derivative. And the most general form of ODEs are called implicit ODEs. And such an equation involves any function that takes as inputs the independent variable t, the dependent variable x, and all its derivatives up to a certain order. In our work, we wanted to limit to explicit ODEs, where the highest order derivative is modeled as a function of t, x, and lower order derivatives. It has been shown that any such expression can be, with some mild conditions, represented as a system of first-order autonomous ODEs. First order because each equation only models first-order derivative, and autonomous because the function takes as inputs only the dependent variable x, and they do not admit the independent variable t. We'll now use this fact to formulate our problem. So we assume there is some dynamical system described by a system of first-order autonomous ODEs. From this system, a solution satisfying all the equations is generated, and we call it a true trajectory. But in reality, our observations can only be made at discrete times and are usually noisy. We call them the observed trajectories, and we assume they can be obtained from the true trajectories by discretely sampling and adding a zero mean noise. We can now collect a certain number of these trajectories to make a data set. And now, based on this data set, our task is to discover the underlying differential equations. Okay, so that's our task. And now let's see how it has been tackled previously. So we start with a symbolic regression, which is a big area of machine learning, and its goal is to discover a closed form function f for predicting labels from features. So we have the usual regression setting where we have where we have a data set of labeled feature pairs, and the task is to find a predictive function f. In symbolic regression, though, we search only among the functions that are closed form. This approach is not directly applicable to ODE discovery because the label, which would be the time derivative here, is usually not observed, so it's not available in the dataset. However, symbolic regression can be adapted for that setting by a method we would call two-step symbolic regression. In this approach, we first estimate the derivatives from the noisy data and create a data set where the derivatives are the labels and the trajectories are the features. Then we can use any symbolic regression algorithm to discover the underlying ODE. But this method has some disadvantages. The main one is that it highly depends on the derivative estimation algorithm we use. Derivative estimations from noisy data is generally a difficult problem, and especially when the measurements are infrequent and the noise is high. And this is very common setting in healthcare. Another similar approach is something we would call a two-step sparse regression, where the first step is the same as previously, to estimate the derivatives to construct the data set. But then in second step, we use a sparse regression to discover an ODE in a linear form. That means that the derivative is modeled as a linear combination from specified functions, such as monomials, x and x squared. And as you can guess, this method has the additional disadvantage of quite limited search space, because there are many important dynamical systems which cannot be expressed in that form. The last approach I want to mention is something we would call a function approximator approach. Its goal is to learn the underlying ODE with a function approximator, such as a neural network or a Gaussian process. And the general idea of the algorithm looks the following. We guess some function f, for instance, a neural network with some parameters. Then we estimate the initial condition. And from that, we solve the initial value problem to compute the whole trajectory. We then compare it to the observed trajectory from the data and fit the loss back to the optimization algorithm. However, it's important to note that the discovered functions are not closed form, so this algorithm cannot be directly used for our task. Moreover, this method is not suitable for chaotic systems, where a small variation in the initial condition results in big deviations in the latter parts of the trajectory. Additionally, the optimization step in itself requires solving the initial value problem multiple times, which is highly computationally expensive. This table summarizes the related work, and as you can see, all methods require either estimating the derivative or estimating the initial condition and solving the initial value problem. And as I mentioned, estimating the derivative from noisy data is hard, and solving the initial value problem is computationally intensive, not suitable for chaotic systems, and sometimes even not well defined. So thus we created Decode to address these challenges, and we overcame them by designing a completely new objective functions that I'm going to introduce a bit later. But first of all, to understand how and why Decode works, we need to familiarize ourselves with variational formulation of ODEs. And this formulation enables us to characterize an ODE without referring to the derivative. This is achieved by introducing a special functional that takes the function f, the trajectory x, and the so-called testing function g. The value of the functional is the sum of these two integrals. And what's important to note is that this expression does not involve the derivative x. Instead, it involves the derivative of g. And if we choose g in such a way that its derivative is easy to compute, then calculating the whole functional also should not be challenging. The variational formulation of ODEs now states that the differential equations hold if and only if the corresponding functionals are equal to 0 for all testing functions that are continuously differentiable and vanishing at the endpoints. And that is why this functional is a core element of our objective. We expect that minimizing value of this functional should correspond to finding better approximations of the true ODE. I can now describe our algorithm. So Decode consists of two steps, preprocessing and optimization. In preprocessing, we take the dataset of observed trajectories and we denoise them and interpolate to get estimated trajectories. Note, we estimate the trajectories, not the derivatives. And our framework is agnostic to the exact kind of smoothing algorithm, and it should be chosen based on the application and the domain knowledge. Then we try to minimize our novel objective presented here. And as you can see, it consists of the functional we defined earlier, and we evaluated on all estimated trajectories from the first step and all pre-specified testing functions. The actual optimization can be done by any algorithm that is suitable for symbolic regression. And this figure shows a comparison between Decode and two-step symbolic regression. And in the latter, first we estimate the derivatives and then use something like root mean squared error to drive the choice of f. In Decode, on the other hand, we estimate the trajectories themselves and then use the novel objective function that does not require derivatives. And as mentioned earlier, we expect that minimizing the objective should correspond to finding better approximations of the true ODE. We actually made the statement concrete and proved it. And in addition to providing a theoretical justification of our algorithm, this theorem guides us in the choice of testing functions. That is, we should choose functions that form a Hilbert basis for the L2 space that are continuously differentiable and vanishing at the endpoints. And the natural choice is the Fourier sine basis, which consists of appropriately scaled sine functions. So now, to evaluate performance of decode, we conducted a series of synthetic experiments. We chose the following for dynamical systems. Now, to generate data for each of the experiments, we first choose one of these systems, and we sample the initial condition from a uniform distribution. Then we solve the initial value problem to obtain a true trajectory, and then we sample from it at discrete times and add independent Gaussian noise. That's how we create our data set. And then we forget about the equations and the initial conditions and try to discover the underlying system based just on the observed trajectories. So we compared decode mainly with 3 variants of the two-step symbolic regression, each with a different derivative estimation algorithm. And for fairness of comparison, we use genetic programming as the optimization algorithm in both decode and all these 3 benchmarks. The main evaluation metric we used was the success probability, so the probability that the correct functional form of equation was discovered. First, we consider compared model and the generalized logistic model. These 2 models are widely used to capture asymmetric growth with saturation. It is worth highlighting that the generalized logistic model involves a constant, theta2, in the power of xt. Therefore, it cannot be symbolically expressed in a sparse linear form, and the two-step sparse regression method cannot discover the exact functional form of this equation. Now, when we look at the plots, we can see that decode achieves comparable performance as the benchmarks in the low noise, small step size settings, where the time derivative x can be accurately estimated from the observed trajectories. However, decode consistently outperforms the benchmarks under the more challenging measurement settings with increased noise or step size. With measurement settings. And with increased noise or step size, the success probabilities decrease much more rapidly in the benchmarks compared to decode. Another experiment we have done was based on the glycolytic oscillator. And this biochemical system consists of 2 ODEs. And compared to the growth models before, the glycolytic oscillator involves more variables and has more complex expressions. We can see that the 2 variables interact in a highly nonlinear way through the term x1, x2 squared. The table shows that decode performs better or equally well compared to the benchmarks in all metrics. And note that decode is the only model that successfully recovered the functional form of the first equation under the highest noise. In the next experiment, we verified that decode is robust to measurement noise even when the underlying system is chaotic and non-periodic, whereas benchmarks achieve high success probability only when the measurement noise is low. The second row shows a simulated trajectory in the phase space using the true or estimated ODEs, and we can observe that decode generates a trajectory that is closest to the true one. Both the SRT and the neural ODE fail to capture the behavior of the system. We also decided to apply decode to model the temporal effect of chemotherapy on the tumor volume. So it is a fact that for most patients, the tumor volume decreases initially in response to the treatment, but it eventually grows again due to drug resistance. And although there exist many models for unintervened tumor growth, few models can capture the effect of chemotherapy or the possibility of relapsing. And in fact, in many cases, exponential equation is used for a crude approximation. We used that data set based on 8 clinical trials on cancer patients. It contains the trajectories of tumor volumes measured over a year in patients undergoing chemotherapy. And we tested both decode and the two-step symbolic regression, denoted by SRT here. And we can see that these 2 algorithms give us qualitatively very different solutions. Equation discovered by SRT is much more complex, and the predicted trajectory is almost constant. The one found by decode is simpler, and it successfully captures the relapse at around 0.6. It also predicts that under no further intervention, the tumor volume would keep growing. The equation discovered by symbolic regression, on the other hand, cannot capture neither of these phenomena. And also, to summarize, we decided to focus on discovering closed form differential equations because we believe they offer many advantages over the black box solutions. They are concise, transparent, interpretable, and can be further analyzed and generalized. However, ODE discovery is challenging because derivatives are not observed, estimating them from noisy data is hard, and solving the initial value problem is computationally expensive and not suitable for chaotic systems. So we address these challenges by creating a new algorithm, decode, that employs a new objective function that circumvents these challenges, performs better than the benchmarks, and is robust to infrequent and noisy measurements, settings which are very common in the healthcare domain. We encourage everyone to check our paper. Also, you can check our code on GitHub, and we're very happy to answer your questions.
Thanks so much, Krzysztof. Okay, so now it is time for our Q&A session. We have a couple of questions already lined up, which is fantastic. And I think actually Mihaela has a question to sort of kick us off. But just to explain the ground rules kind of once again about the Q&A sessions, as always, if you have a question, please post it into the Slack chat. I think we could probably take a couple more questions than we currently have now. So if you did have any questions about the presentations you've just seen, please do feel free to put them into the chat. When we've chosen you to ask your question, we'll ask you to unmute yourself. Please do so, and then try to ask your question, hopefully within the space of about a minute, so that we can get through as many of these as possible. And then when you're done asking your question and you've got your answer, please just remute yourself so that we don't continue to hear you through the rest of the session once your question has been answered. So I think, Mihaela, if you did have something to get us started off with, please feel free to go ahead and ask that.
So I have a question for either Zhaozhi or Krzysztof. So you presented this work that we have done, but what type of data sets you think we need to have, and what type of problems you think this type of methods can address? Can you say something about the generality of the method and the type of settings where it applies?
Yes, so for decode, it applies to scenarios with, so it applies to data sets that are potentially irregularly sampled time series. So for instance, the observation of biomarkers, the longitudinal observation of biomarkers over time is a good example. But of course, the exact scope of the problem needs to be defined by the modeler, and also which variables to include. And also the time series can also have control covariates, like the treatment or interventions. It can also incorporate static features like the age or sex, ethnicity, and so on. Yeah.
Fantastic. So, Mihaela, do you think we should go to some of the questions that we received? Okay, brilliant. So I think the first one is from Jason. I think, Jason, you've actually asked a couple, but if we could just go to the very first of them, and then I think we may try to circle back to you sort of once we've got through a couple more. I think the first question you asked would be probably a good one for Zhaozhi to answer. So if you wouldn't mind unmuting yourself and asking.
Yeah, sure. My question is, what's the difference and the connection between multimodal optimization and multi-objective optimization? Both are two concepts you mentioned. Thank you.
Thank you. So for multi-objective optimization, we are simultaneously want to achieve multiple objectives, like minimizing the goodness of fit, minimizing the loss, like RMSE, and also minimizing the complexity of the equation. So there we have different functions. You can think of it as minimizing a vector value function. In terms of multimodal optimization, so this is, I didn't actually properly define this term, so sorry about that. So this refers to the situation where multiple local optimal exists. So we're dealing with non-convex loss functions. So maybe one local optimal here and another here, and which makes the landscape of the loss function multimodal in a sense. Yeah. Hopefully that clarifies.
Yeah, but that's like the multi-objective, like a convex. So intuitively, I think the multi-objective also non-convex, right? So do you use like a weighted combination to incorporate those different objectives? Like how do you balance it?
Yeah, there are different ways. One way is to do the weighted average, and it's but this approach has limitations. How do you decide the weight a priori, right? There also works on Pareto efficient optimization that tries to obtain the Pareto front of all the objective functions. Yeah.
Okay. So if you don't mind, I think we'll move on to our next question, which I think was from Elizabeth. And this is probably maybe a good one for both Zhaozhi and Krzysztof, I think. Sorry, go ahead.
Yeah, hi. So I'm Elizabeth, and my question is, so in the case of biomedical signals or images where you have high input dimensionality, and there are many features, and those features in themselves don't have a lot of meaning, so they are only interesting once you look at the global image. How can we apply these kinds of methods? Is it possible to derive equations with, for example, decode? Or should we first derive some global features of the signals, which will lead to information loss, I think, but maybe a more tractable problem? Or is there another approach that would be more appropriate? For example, unsupervised clustering-based approaches or self-supervised learning, maybe?
Yeah, thanks for the great question. So for image, I think the challenge is that if we're dealing with raw images, we're just presented with pixel values. And these pixel values may not even have strong semantic meaning. For instance, due to the translational invariance, if we move the camera a little bit, the pixel may capture completely different things. So in order to make the equations, if we demand a more kind of transparent and kind of interpretable common equation, I think we need to work with more high-level features to start with. And yeah.
All right, thanks.
Krzysztof, did you want to add anything to that, or is it?
I think Zhaozhi summarized.
Okay, brilliant. All right, so I think we have another one. Up next is Igor. If you're able to unmute, I think this is probably, again, one that can maybe be answered by either Zhaozhi or Krzysztof. But please go ahead.
Hello, thank you for the presentations. Yeah, my question about the decode method. So you were showing those examples with the Lorentz attractor and other, like, let's say, maybe toy examples, where the input is rather low dimensional. So my question is, did you have any experiments, or like maybe you could comment somehow on how the method scales computationally, for example, to a larger dimensionality of input? Let's say if you consider like tens of hundreds of like clinical variables, for example.
So I guess I can. So you're right that we tried it on mostly examples with low dimensionality, and I think it is mostly because the symbolic regression algorithms are the bottleneck. So we use genetic programming for our task, and this kind of algorithms still do not work well with very high dimensional data. And we actually believe that this should be a direction some part of machine learning community goes to go and develop these algorithms so that they can become better and cope with more dimensional settings. Yes, Zhaozhi, do you have anything more to add?
Yeah, just to come back to the optimization perspective I presented. I think the key challenge here is that genetic programming as an optimization algorithm is not so efficient to search for discrete equations when there are lots of variables. And this is something that, as Krzysztof mentioned, we think that can be further improved on. But I think the same objective function, the normal objective functions proposed by decode can be used as well if we updated search optimization algorithm. Yeah.
All right, thank you very much.
Okay, brilliant. So I think we have another one from Zara. Zara, again, I think this is possibly one that both of you might be able to weigh in on. But Zara, if you want to go ahead and ask.
Yeah, sure. Thank you very much. Thank you for your presentation. Yeah, I wonder if you have tried your method on multimodal data, because in healthcare, especially, data may be collected from different resources, time series, images that are irregularly sampled through time. Do you think your method can benefit from both of them efficiently, or is there any kind of bias on a specific type of data? Thank you.
Which of you wants to try and tackle that one?
Yeah, very good
thanks,
question.
Zhaozhi.
So at the moment, the decode only focuses on the time series scenario. It doesn't really consider modeling images. But I think in the future, we're also actually looking into developing different sorts of different equations beyond ODE, and this type of equations like PDEs may be more suitable for handling kind of higher dimensional spatial, for example, correlations. And this is actually ongoing work, I would say. Thanks.
I think I can also add, maybe because it slightly connects with the previous question, that, for example, with biomedical data, I guess you can imagine if you can somehow extract these higher order features, and then if they behave in some kind of dynamical way, so that it can be modeled by some kind of dynamical system, then obviously this can be combined with our method. And what's very interesting about our method is that it's very applicable also to systems where these different variables can interact with each other. So these ODEs can be like, I'm not sure if the word is coupled, but the equation can depend on all different variables from all different coordinates. So definitely it is possible to use it with different modalities.
Thank you very much for your answer.
Okay, so I think we only have time for a couple more questions. The next one, I believe, is from Prajwal. Prajwal, I think you're still with us, so if you want to unmute and ask away, please go ahead.
Yeah, thank you for the presentation. I was wondering how this decode technique is better or stands out good in front of Cindy technique, which uses sparse regression model. Like, I was wondering if this technique can apply to the latent variable also, like if you give only measurement for X dimension in case of Lorentz model. So does it still works?
And I didn't actually think of which of our two presenters should actually answer that, but thanks, Zhaozhi.
So Cindy is actually one specific incarnation of the two-step symbolic regression or two-step sparse regression, because in Cindy, I think the authors proposed to use some common basis functions like polynomials and to fit a standard regression problem on estimated derivatives. So we actually included several incarnations of Cindy as benchmarks. Can you remind me the second, the one with latent
for the latent variables, hidden variables or latent variables?
Yeah. So yeah, this is also one direction that we want to pursue further. So for the current version of decode, it doesn't really handle latent variables. But it is possible to use decode to model, for instance, second order or higher order ODEs. So that part is possible. Yeah.
Okay, thanks.
Brilliant. So I think we only have time for one more question, and that one will probably need to be done relatively quickly at that, because we're approaching the end of this session. So if I could call on Jason again, I think you had like maybe one or two more questions, but if you could just try to help us squeeze it into the last minute or so, that would be great.
Yeah, I think my colleague asking what's like the future trend in the intersection between ODE and deep learning, and what's the disadvantage using deep learning to solve ODE? Yes, thank you.
Yeah, I think thanks for the question. It's very interesting. So ODE and deep learning is it's actually quite a very hot research area. I'm not sure I can summarize everything in 1 minute, but so I think one promising aspect is to work on what is the kind of the best neural architecture for modeling ODE. Because in the original neural ODE paper, the authors use multi-layer perception, and in later papers, people found that this is probably not the best architecture. And also another interesting aspect is to use to model different type of differential equations beyond ordinary differential equations. And there are some very exciting work on controlled differential equation and beyond. I think using deep learning to solve ODE is completely kind of a parallel line of research. And in that research, that aspect, we have a known ODE or known PDE, but we don't know how to efficiently solve it. And this is quite different from inferring an unknown ODE from the data. So actually, there are also, I think, a few recent works that uses deep learning's universal function approximator approach to help. Essentially, they use ideas of amortized learning. So they pre-train a network to recognize the input and output pairs of these PDEs or ODEs and kind of use machine learning to generalize. And this, I think, is also an interesting research area. Thank you.
Thanks so much, Zhaozhi. Okay, so I think that brings us pretty much to the end of today's session. And before we sign off, just sort of a little bit of housekeeping from our end. So firstly, regarding a sort of refresh to the format and content of the Inspiration Exchange sessions going forward. And Mihaela, if you want to say maybe just a quick thing about that,
yes,
please go ahead.
But before I say that, I wanted to say that I want to tell everyone that I'm extremely sorry that we will be losing Nick in our lab. He's going to be moving to some other endeavors outside the lab, unfortunately. And I'd like to thank him very much for everything that he has done in these past 2 years for me, the lab, Inspiration Exchange. To be very difficult to go on forward without him. So I want to thank you very much, Nick, for everything, inclusively for helping me start Inspiration Exchange, and very, very thankful to everything that you have done for us.
Not at all. And sorry, before you continue, I guess I should kind of, not rebut, but reply to what you said. So thank you very much. Also, thanks so much to our lab members as well. It's been an absolute pleasure and a privilege to work with a lab that's producing so many amazing and impactful new ideas. And I'll keep following everything the lab's doing. I expect great things of you. I'm sorry, I'll let you continue now.
Thank you. So, well, with this being said, we are going to continue with the Inspiration Exchange, and we are going to continue in a new format. First, currently our engagement session is mainly focusing on engagement with machine learning students. We plan to add to this community professionals interested in healthcare. So besides students, we plan to get researchers in industry, researching in academia that are a little bit more senior to engage with us. We also plan to have brief tutorials at the beginning of sessions, bringing state-of-the-art research at the forefront. So currently we are directly jumping in a particular topic and providing relatively little overview of where the area is at. And we believe there will be a lot of help in really putting more context to these discussions. So we are going to start in the future with a brief tutorial on state of the art in the particular topic that we are going to discuss. And finally, we plan to bring various industry leaders to join our inspiration exchange to discuss with us and with you about these topics and think together how we can bring these topics forward such that we can really make this transformation in healthcare using machine learning. So hopefully this new format will be even more exciting, hopefully, because it will provide more interaction with others working in the field at a more senior level, and we will have more interaction with them as well. So I hope you'll continue to join us.
Thanks very much, Mihaela. And I'm very much looking forward to seeing the new format and the new content in action as well. And just a final note, so we are still recruiting for PhD studentships as well, starting in 2022. This is very easy to sign up and register your interest for. Just visit our website and click the Join Us button here, and then just fill out the form that's on the page, on the Join Us page, basically. And just some very final housekeeping. So obviously we will be editing and uploading today's session. So that'll be available on YouTube soon, and you'll get this via email. The next session will be on the topic of causal deep learning, and this will be on April 14th. And again, more info about that will be shared via email over the coming days. And that'll be the first session to kind of feature parts of this new format that Mihaela just introduced. Also, we now have an email address for the lab itself. So the next email related to Inspiration Exchange will be coming from the Schaar Lab at dampt.cam.ac.uk. Don't be surprised if it's not coming from my personal account, but this one instead. It is still very much from our lab. In the meantime, of course, if you want to stay up to date with Inspiration Exchange, just visit our dedicated page for these sessions, and do let your friends and colleagues know about Inspiration Exchange. It's very important that we be able to build this community with your help. And thank you very much to everyone who has joined, I guess, not just this session, but all our sessions in the past. Thanks so much to our lab members and to Mihaela for making these sessions what they are. And I will continue to watch these sessions from somewhere else in the near future, and I look forward to continuing to see this series develop further. In the meantime, please all take care, stay safe, and all the best.